Alright, and welcome to the third episode in the 16-bit breadboard computer series that I'm currently doing. Today we are going to be building a program counter, as I said in the last video, so I'm going to prepare the breadboards for that. And it is going to be using the synchronous up-down counters, the 161s I talked about last video, to do the program counter. So I'm going to be using 6 of these to get the ginormous 21-bit program counter, 22-bit program counter used for the system, and it will have all the operations needed for the entire computer and its uses throughout it. So I hope you enjoy, and let's get into the build. So these are the 3 signals from the output of the program counter main clock that's used, the control output, which I will explain in a second, and the actual program counter bit that we will be looking at. So the control output, the most complicated thing, is a circuit that decodes when we want to pulse the program counter up, and with the settings I have right now, I have RAM on and data on, so this is when it's pulsing, but I can change it, and that will be used to make it a lot more flexible to change how the program counter is pulsing, meaning there will be a lot more different instructions, so I don't have to take a full 64-bit instruction, which would be RAM, data, and instruction. I can take a 32-bit one if I just need data and the instruction. You know, it's not as complicated. And vice versa, I can do a lot more things with this, and it makes it a lot more simple. This signal is just the output of the first bit of the program counter, so that would be used to get output from the program counter. It's just used here to corroborate that the thing is working. Yeah, so this is the outputs, the verifiability of the circuit, making sure it's working. Let's get into how the circuit actually works. Alright, so this is the circuit for the program counter. I added a halt control signal to the circuit by ANDing the oscilloscator output with the halt signal. It's just a simple AND gate, and that uses, everything else uses that, including the clock decoder, the clock divider right there. And then all of this other stuff is just delay for the combinational logic circuit, which I will talk about in a second. But let's talk about how the program counter works. So pins 1, 2, 7, and 9 are all connected together, and those are the clock pin, which is pin 1, or pin 2. The clear pin is pin 1. Pin 7 is the CET pin, which is part of how it ticks forward. And then pin 9 is the load pin, so it will load values, so you can do jump instructions. And then pin 10 is actually connected on all of them except the very first one is connected to the pin 15, the ripple carry output of the one. So this one's pin 15 ripple carry output is connected to this one, and so on and so forth for all of them. This one, ripple carry output, isn't used. And that is so that whenever one of them goes to its full value, the next one will be pulsed, and it will go 0, just like how it behaves internally, and that's how they're strung together. Except for the first one, the CET, and that other one, pin 10 there, is connected together to the pulse signal, the counter enable signal, which is connected to the combinational logic, which I will now describe. So the way it works is I use this. It's a 161 counter as well. It just is constantly running, and it will be controlled by the control word, but that is a lot farther in the future. It will be controlled by that circuit. But for now, it's just constantly running, and it pulses, and these 3 pins, these 2 are, I got inverted multiplexer data selectors, but you don't have to. I got 150, 74 HCHD 158s. The circuit will work basically the same if you use 157s. It just means that this signal is normally inverted, so it's high on low and low on high. But if you use 157s, it would be standard. It would be high on high and low on low. This one is standard because they cancel each other out. This one's just on the second inverter, a second multiplexer. And so what they do is, this is the first step connected to pins 2 and 3, and it just selects between those on the first output of the program counter. And these program counters are in the opposite way we expect to see values. So, and the highest value is actually closest to the right, and the lowest value closest to the left. And that was pretty annoying when I was wiring that up, because I got it wrong and had to rewire the whole thing. But now I have it all fixed. Just keep that in mind when you're building this, because it could be really annoying if you mess up. So the first output goes to this one, and it selects between the steps 0, 1, 2, 3, 4, 5, and 6, and 7. And so basically those are the 4 steps. And this is the first one. It's either 0 or 1, depending. So if it's 0, if this is 0, the select pin, it will output 0. And if it's 1, it will output 1. And then this one is a little bit different. If it's controllable, so this will be controlled by a bit in the instruction to know if it needs to read data, and then it's against ground, so it will either be 0 ground or 1 in ground, depending on what you put in. And so that's that one. Nothing else is needed because everything else can be ground for it. Then the second one is the second program counter output, so bit 1, if the first one is bit 0. And that's the select bit for it. And then it selects between the 2 outputs from the last one on the first selector and the 2 inputs, and then this RAM signal, which is inverted, like I said earlier, and power here, because that needs to be inverted as well. It should be ground, but it's power, so it can be inverted. And then those 2 output signals go into the custom-made multiplexer up here. I'm just going to move these so you can see this a little bit clearer, and if you need to build it, that's how that looks. Up here, this is a lot of delay. I think I use 2 inverters, 2 AND gates, not 2 AND gates, 3 AND gates. Yeah, 2 inverters, 3 AND gates, and an OR gate. So 6 gates in total to get the delay I need for the circuit. Maybe it'll go down or up, and I'll check it as the circuit gets more complicated, but I use 6 gates to delay it, so you don't have to use this exact combination if you want to here. You can look at it. I'll take some of this away. But it's 6 gates delaying the output signal from this combinational logic circuit. The final one is another selector. It's down here. Basically, these are custom-made multiplexers because I only need one. I'm not going to put in a chip in just for one. So the select bit gets inverted. And then this is an AND gate. It gets ANDed the first signal from down here. And then the inverted one, or the non-inverted one, gets ANDed with the second one from down here. And then this and this get ORed together to get the final output, which is delayed, and which get the final output. These are all delaying the clock signal. The final output is going down to here. And so that's kind of how the main circuit works. I'm just going to explain more what's going on here because this might be hard to see. So this is just these outputs are being connected and switched around, like I said, so that the first bit is first in the first bit is actually first and the fourth bit is actually fourth. So they're switching them around and getting their bus transceivers, so 74 HC or AHC 245. This is 161. These are all 161s. This is these are 2 AND gates, so 08s. This is a 04 inverter. That's a 161 as well. And this one is a 32. Yes, it is a 32. Those are just all the logic gates they used, if that was unclear. And I'm going to put in some green LEDs for this at a later time. I just didn't have the LEDs. You can see some of them here. But this is just those wires connected up. And the right wires are also backwards as well. So you will have to switch that. Keep that in mind when you're building it. And this is the program counter and output signal. It's inverted, active, low, and these 2 wires connect it for all 3 of these. And this would output to the buses, the address bus and the data bus. And then this makes the direction of these transceivers going this to there. So if it's high, it will be outputting, and if it's low, you can still write to it via the load signal. Let's talk about a load signal. So in the actual circuit, I'm going to have something in the control word that will multiplex the load signal and the clock. So that way it won't load some weird value if it's doing something in the middle of something, and that way it will only load the value that you want it to. That will be implemented in the control word circuit, which is a long time in the future. Just keep it in mind, this isn't going to be the final load signal. It will be changed, as well as this is not going to be the final clock. It will be changed at some point in the future, and I might take the number of gates down as it will be delayed further in the circuit that's selecting which clock you will use. Either the standard clock or the faster 10 megahertz or even 20 megahertz if I do overclock clock. And so that is the main circuit for this build. If you have any questions, leave them in the comments below. I will try and answer them and do questions. I'll answer them in the next video before we get into the build, try to explain exactly what's happening more. So I hope you enjoyed. Please consider subscribing. It really does help me out. See you next time.